Today we're going to pick up where we left off in section 11.1, and you can use April 28th if you need to redate your notes. In our last lesson, we talked about the model for multiple linear regression. When we test in simple linear regression, our null hypothesis states that any particular slope, beta sub j, is equal to 0. And if the slope is 0, then there is no linear relationship. We're going to do the same type of test for our multiple regression. So in multiple regression, we're not just testing one slope beta j, we're testing all of them. So if you fail to reject the null hypothesis in multiple regression, really it just indicates that the variable you tested might not be needed in the model that you're using. When we set up our null hypothesis for multiple linear regression, we're running a test on all the slopes. However, not all slopes will show up as significant. So your alternative hypothesis says that it would be safe to throw at least one away. But what we want to do is really analyze the model as a whole to see which variables are really contributing to the model and the prediction. In our last section, chapter 10, we looked at simple linear regression and we did learn about the f-test. We learned that the f-test was also equivalent to the t-test if we square it. And remember, for the f-test in the distribution, you're in the upper right-hand tail. And the further you are to the right, the more evidence against the null. Now, since we've moved on to multiple linear regression, when we look at the ANOVA F statistic, we are testing this hypothesis that all the slopes are equal to 0. Our alternate hypothesis says that at least one is not 0 and must be contributing to the model itself. We're going to compute the F statistic the way we did in chapter 10. We're going to look at our ANOVA table, and it will be the mean square for the model divided by the mean square error. When we look at our ANOVA table, we will have a list of p-values. Some will have significance and some will not. But basically, we're stating that at least one does have some kind of influence on our response variable y. So this is our ANOVA table. The sum of the squares is still calculating the same as it did in simple linear regression, but in our degrees of freedom, we have some changes. For the model, P represents the number of individual variables present. So if you're checking to see if height, weight, and gender all affect your IQ, height, weight, and gender are 3 variables, and it would be 3 degrees of freedom. The error will be the sample size minus the number of variables minus 1. And the total degrees of freedom is always n minus 1. So knowing at least the model, we could work backwards. The mean square, calculated the way we did in the previous examples. So we would take the sum of the squares model and divide by degrees of freedom model, sum of the squares error divided by the degrees of freedom error. There's our F statistic, and the p-value will be calculated on the calculator like we did in the last chapter. If you want to come up with a value for variance or sample standard deviation, we're going to use the mean square error. So variance is the value you see for mean square error. If you want standard deviation, you would have to square root. When we input our data for simple linear regression, typically we create a least squares regression line, and then we look at the value of R to see how tightly correlated they might be, and then R squared would tell us what percent of the variation is due to the model. We're going to do the same thing with multiple regression. We call it capital R squared. And again, it will represent the amount of variation due to the model. And the model is going to incorporate all the variables as one whole. So to calculate capital R squared, again, we could do it by hand. We typically will not. We'll use our ANOVA table. So we'll use the sum of the squares model divided by the sum of the squares total. So again, when we look at the value of R squared, they're taking the model with all of its variables together. So it's looking at it as one full unit. If you do take the square root of R squared, you'll come up with the multiple correlation coefficient. It would be equivalent to R in simple linear regression. We don't always do this. It's rare that I've seen it, but it could be found. All right, so our first assignment today is going to be 11-12. You're going to do part A, and I'm going to ask you to build an ANOVA table, and you can take it all the way to P. We're going to skip B and C because they'll be incorporated into your table, and then go ahead and do part D separately. What I have here are a couple Minitab output. And just to show you, we're going to build our own ANOVA tables and our coefficient tables. But in this first example on the left, they're looking at PIQ. That's going to be the response variable. And the three individual variables that are part of the model are brain, height, and weight. Now, we don't know what any of this means. This could be on humans. It could be on animals. We don't really know. But you can see that the regression has 3 degrees of freedom, and each of the brain, height, and weight consists of one of their own degrees. We can see that there were 37 total degrees of freedom, which means the observations N is 38. And then they go through the table. So this is provided. You can see the p-values, though, for each of the individual variables. Brain is significant, height is significant, weight is not, assuming that we're using alpha at 0.05. The coefficients table down below, the constant represents beta 0, and in the order they're listing, brain is beta 1, height is beta 2, and weight is beta 3. The coefficients represent the slopes for that variable, and they're providing the standard error for those variables, the t statistic, and then the associated p-value. So again, these p-values are the same as they were in the ANOVA table up above, and they've also provided the regression equation. So you can see based on how they're listing it, this is beta 0, beta 1, beta 2, and beta 3. And you can use x sub 1, x sub 2, and x sub 3 instead of the actual name of the variable. They've also got another table here on the right. They looked at the final exam and want to know if exam 1, 2, and 3 are good predictors of how it will turn out in the end. So they're listing the same information. We have the ANOVA table with the p-values. We have our coefficients table with all of our slopes, t-values, and those associated p-values, and we have the regression equation. We're going to go through and do an example, and we'll have your iPad generate the coefficient table and the ANOVA table for you, and we'll come up with our multiple linear regression model. So the sample data that we have came from the Internet Movie Database, and what they're looking to do is see if they can predict the total revenue for any particular movie. So at this time, if you want to pause the video and input all this data, you don't have to put the title of the movie, but keep this in order. Now that your data is in, we're going to go through and generate the least squares regression line for the sample. So what you'll want to do from the spreadsheet is select your wrench. You're going to choose statistics, stat tests, and you might want to scroll through the list, but you want multiple regression tests. The first thing it's going to ask you is how many individual variables. We have 4 contributing to revenue, so you can change that value and hit OK. And then it's going to ask you for the Y list. The Y list is the revenue, so we'll select that. And then it's going to go through the X list. You want to keep it in order. I've also put the values here in the table. So your X1 is budget, X2 is opening, X3 is theaters, and X4 is opinion. And then you can designate where you want the results. I'm going to put mine in column G. What you can see in the results column, it's going to start with the model for the regression equation, and then it goes on to give you the F statistic and the p-value. What I want to do right now is jump to the coefficients table. So I've got them listed in order. The coefficient list, if you scroll through, is going to be the B list. So if you find the B list, select the cell that has the values, and in order, starting with beta 0, they're going to list then beta 1, beta 2, and so on. The order you put them in is important because that's how they're going to display them in the cell. So if you want to take a minute and fill those in, the next thing we're going to look at is the standard error for the coefficient. Same thing. You're going to find SE. You know what, before we move on, this is our least squares regression line model for our movie theater information. The predicted revenue. So I have in order the constant, I have the slope for budget, and then I've designated X1 to go with budget. The slope for opening, beta 2, goes with variable X2. Slope for theaters, and the variable X sub 3. And finally, the slope for opinion. Now we're ready to go on to our standard error. So you're looking for the SE list. So you might have to scroll through your iPad a little bit, select the cell that has all the results, and same thing, it's going to maintain the order that you input your variables. So if you want to take a minute and plug those in. Then we're going to move on to the T list. The T list has done all the T tests for you. So again, in order, we're going to list those. And then we're finally moving on to the P list. Same thing, you want to select the cell and the value of the P result is listed in order from beta 0 through beta 4. At this time, we want to see if any of these values are significant. So the constant's not really playing a role, not the budget. The opening has a p-value of 0. That's significant. The theaters that it plays in, not really a significant issue, but the opinion does matter. So those 2 values actually are important in the model. The other 2, because we're not going to throw the constant away, the budget and the theaters, we might look at removing those, generating a new model, and see if it's any better. Now let's set up our ANOVA table. This is already present in your results on your iPad. So we always start with the model, which is listed as regression on your iPad, and we have error and total. So degrees of freedom, for the model, we had 4 individual variables. And then we had 14 movies that we examined. So I know degrees of freedom total is n-1, and that allows me to come up with the error. On your iPad, it also says degrees of freedom regression is 4, and degrees of freedom of error is 9. So those values are present, even if you had trouble coming up with them on your own. We're looking at the sum of the squares. So on your iPad, if you look for SS regression and SS error. And I did total. This total is not present on the iPad. The mean square is also listed, although we can calculate it by hand. If the data is available, you can go ahead and use it. So we're looking for MS regression and MS error, and we can fill those in. We don't need a total. The F statistic is calculated by dividing the mean square model divided by the mean square error, but this is also present at the top as our F statistic. And then our p-value, if you look at the iPad, it looks like it has a value of 5.84, but when you select the cell, you can see that it's scientific notation, and it is essentially 0. One of the other things you might want to calculate is the sample standard deviation. So I did take the square root of MSE. So there's my standard deviation for this sample. And if we want to look at the variation due to the model, we might calculate R squared. So remember, this is the sum of the squares model divided by the sum of the squares total. 99% of the variation is due to the model. That is extremely good. So this model seems to be a good fit. Our second problem is 1120. I'll have the twister data present when I send this out. And at this point, if you have any questions going through notes or working on your homework, make sure you give me a call. Otherwise, have a great day.